So, okay, I was just writing, so I've started recording, good. So just writing, the first thing we're going to do, today we're going to do sort of the beginnings of NP completeness. We're not going to get to Cook's theorem. We're going to get close to Cook's theorem. But the thing is, usually people start NP completeness with Cook's theorem, which is kind of a shock. I want you to understand where it came from. I don't just want it to drop from the sky. I want you to see that this was actually, I mean, obviously Cook is a brilliant guy, but this was not just some stroke of genius that came nowhere. This actually, it makes sense. And if the rest of us thought long enough, like probably a really long time, we might actually do this ourselves. Because it's not that bad, okay? It is sort of pretty much sort of the hardest thing you're going to see in this class, and people say that this class is pretty much the hardest course. This course is pretty much the hardest course in the BCS degree. But I want you to understand that it's not really as bad as people make it. Okay, so again, we're talking about reductions because I love reductions. Reductions are super cool. Remember, I think in one of these things I said that reductions are like the force. They bind problems together. Problems which look completely different, you manage to find a reduction that says, yeah, okay, if I can solve this faster, I can solve this faster. So let's start out with three famous natural problems, and these reduce to each other fairly easily. And usually this is what people put on exams and things like that. I don't, because I think they're too easy. So clique is the problem given a graph, given some graph. Right, so you have, I'm using blue because the black marker is dying. So you have some maybe it's planar, maybe it's not. Okay, so here, so you're given some graph G, and you're given some K, some integer K, and you're asked, is there a K clique in this graph, right? So if K equals 3, is there a triangle in this graph? Yes, obviously. And here's another one. Here's another one, right? So what if K equals 4? Is there a 4 clique? A 4 clique looks like this. Right? So, can you see this? I hope so. I have like 13 students, that's it. Okay, and possibly that plus 9 is including me. So this is a 4 clique. It means you have 4 vertices and they're all connected to each other. Is there a 4 clique in here? Is this one is connected to these two and this one? This one is connected to 1, 2, 3. Yes, 1, 2, 3. Yes, there is a 4 clique. Look, this is a 4 clique. Okay? So obviously, if I give you a graph on n vertices, and I say is there a clique of size k, you can do it in time n to the k, because n to the k, roughly, yeah, pretty much. N to the k times k, maybe, if you do it completely naively. So you just have to, maybe k squared. You just have to, enumerate all the possible subsets of k vertices. How many are there? There's like the n choose k, which is bound n to the k. Okay? So the thing is, k has to be a variable here, Because if I give you a graph on 1,000 vertices, and I ask if there's a clique, if there's 100 clique in there, you don't want to be doing something like 1,000 to the 100. That, it's not polynomial in n and k. Remember when we were talking about factorization, we said polynomial time algorithms, they should run in time polynomial in the size of the representation of the input. So k, when I write k, I'm going to use log k bits. So I'm not allowed to use I'm not allowed to use O of k time even, although since I have the graph and it's n vertices and k is bounded by n, then I actually can, but that's not because that's not, okay, that's because it's polynomial in the size of the graph. But definitely n to the k is out. So this is clique. Given a graph G and an integer k, is there a k clique in G? That's a subgraph. Does everybody see that? Everybody understands what the problem is? So, independent set. Is given a graph G, wait, how many? This is going to be a mess. This. Okay, so this one, 1, 2, 3, 4, 5, 6. So there are 2. So this one goes to this one, and then goes to which one? 1, 2, 3, 4. All right. Okay. So that's it. Okay. This is it's going to take me a second to work this graph out. 1, 2, 3. 1, 2. All right. Okay. So everything should have 1, 2, 3, 1, 2. 1, 2, 3, 4, 5. Yeah, that's good. 1, 2, 3, 4. But 1, 2, 3. No. Okay. So here is another graph. Okay. And an independent set is like the opposite of a clique. It's a set of vertices. So I'm given a graph G. Let's call this G prime. And I'm also given a k. Here, say k is equal to 4. Let's say 3. And I ask, is there a set of k vertices such that no pair of those k vertices are connected to each other? Okay, so here, can I find 3 vertices such that they don't have edges between them? Yes, like this one, and this one. Right? This one's not connected to this one, this one's not connected to this one's not connected to this one, right? So that is a set, so this has an independent set of size 3 as a subgraph. Okay? So that's the problem of independent set. Everyone understand what so again, obviously I can do that if G prime has n vertices, then given G prime and given K, I can check it. I can check to see if there's an independent set in something like n to the k time, because I just check all the possible subsets and check if they're independent sets. But that's not polynomial. That's not polynomial in K. Right, the exponent is k. So, can you see a relation between these problems? Anybody? If I gave you a magic box that could solve clique, could you use it to solve independent set? Yeah, they are. So if you have this magic box, so let's say you have this magic box. I should replace the black marker. You have this magic box that says solves clique, right? So this is a box, and you drop in a piece of paper with an instance of clique on a graph and a number k, and out will drop another piece of paper that will say yes or no, and it will indicate whether or not the graph has a clique of size k. Okay, so oh, by the way, I should mention that these, for the moment, we're going to be talking about decision problems. Decision problems, the answers are yes or no. Okay. Somebody remind me to get into this later once we're finished all this NP stuff. So if I gave you this machine, what you would want to solve, and you wanted to solve independent set. You didn't, for the independent set, you can add all the edges that aren't there and remove all the edges that are there. Yes, exactly. So that's what we would do. We would build a box that says independent set to clique, right? And so now, if you drop in here a piece of paper that has a graph G prime and a number K on it, out will come a piece of paper that has a different problem, has an instance of clique on it, such that, right, so we have a piece of paper that has G prime and K, and out will fall a piece of paper that has some graph G, and, well, okay, so it's going to, let's call this K prime. It turns out that at the moment, K prime is going to be K. Out will fall a piece of paper with an instance of clique, and this will solve clique. So what do we want? We want that this machine takes the instance of independent set and outputs an instance of clique, such that the instance of clique is a yes, if and only if the instance of independent set was yes. So G prime has independent set of size K prime if and only if this is written IFF, G has clique of size K, right? So if we can build this, machine, and I give you this machine, then you have altogether, this solves independent set, right? And I should say that obviously you can solve independent set, as I said, in time n to the k, so you can solve it in exponential time. We wanted to suppose if this machine works in polynomial time, and you can get this machine to work in polynomial time, since the composition of two polynomials is a polynomial, you will be able to solve independent set in polynomial time. Okay? So, can you read this? Not really, no. Try it. Okay, yeah, it should be, it's just I'm running out of, I can't really get a third whiteboard. Can you read this stuff? Okay. So it says G prime has an independent set of size K prime if G has a clique of size K. Okay. So, I will take a picture. I will trip over the cable. Is it IFF? Yes, because IFF is short for if and only if. My mother used to proofread my papers. She really objects to that. She thinks that mathematicians shouldn't be allowed to make up words like that, but we do. They do. I'm not really a mathematician. Okay, so I'll leave this here. I'll try not to accidentally drop my camera. Okay, so how do we build this machine that takes an instance of independent set and outputs an instance of clique? Well, it's not that hard in this case, because I actually did it as an illustration here. What we do, we take, as was observed by Gabriel, we take every edge that's there and we erase it. So here, if these vertices were A, B, C, D, E, F, A is connected to B in G, so A, B, C, D, E, F, so A is not connected to B in G prime. A is not connected to D in G, so A is connected to D in G prime. Okay, so this is called taking the complement graph. So if you take a complement of a graph, you switch the presence or absence of every edge. So if you take the complement of a clique, you get an independent set, and vice versa. So if G has a clique of size 4, then G prime has an independent set of size 4. Well, okay, I asked about 3, but it's actually 4 because here this is a clique B, C, D, F. B, C, D, F. None of these 4 are connected to each other. Well, let's make this a 4. That's how you build this box, okay? So we now, and obviously this takes polynomial time. Given a graph G, you can switch the status of each edge in polynomial time. I mean, how many edges do you have to consider? Why is my lamp flickering? How many edges do you have to consider? Well, if you have n vertices, it's at most n squared possible edges, so it takes polynomial time. Okay, so this is a reduction from clique to independent set, and so here, independent set to clique. Given an instance of independent set, we turn it into an instance of clique. Oh, here, because this, I don't think this has a clique of size 5. I don't see one. No, it doesn't. Normally somebody gives you the graph. So someone's asking why k is equal to 4. K is just a parameter. K is a part of the input, not exactly a parameter. You're given the graph and you're given k. So if I ask you k is equal to 4, you can do it in n to the 4 time, but this isn't polynomial in k. And you can do it in n to the k time. That's not polynomial in k. So if somebody gives you a huge graph, they might have k is equal to 20. That's asking you, is there a subset of 20 vertices, all of which are connected to each other? K is just part of the input. It's like G. Why does the graph look like this? Because it does. You don't get to ask, why is the input like this? It's not part of our job. We take the input and we deal with it. Sometimes we ask, but ultimately, whoever whoever our employer is allowed to give us the inputs, and if we've guaranteed we can solve the problem, we better deal with the inputs they give us. So that was pretty clear. Now, so that's our first reduction of the day. So now let's consider the problem of vertex cover, which we have seen before. We love vertex cover. So for vertex cover, you're given a graph, let's say this one, and you're given another number, so this is k prime, so you're given a g, and you're given a k, and you're asked, does g have a vertex cover of size k? So that means, remember, a vertex cover is a subset of the edges, is a subset of the vertices, such that every edge in the graph is incident to one of those vertices. Okay? So, for example, what could k be here? So let's say k is equal to 2. So k is not always equal to 2, okay? But they are allowed to give us this k. Now, obviously, if there is vertex cover of size 2, there is also a vertex cover of size 3, 4, etc., up to n, because you can add vertices to the vertex cover, and it's still a vertex cover. It's not necessarily then a minimum vertex cover, but it's just asking, does G have a vertex cover of size k? Well, does G have a vertex cover of size k? Well, notice that if I consider this independent set, and then I take the complement of the independent set, I get a vertex cover. Why is that true? Because if I have, is this just luck? So if you have an independent set, there are no edges between those vertices. So if you take the complement of the independent set, then every edge in the graph, now you take all the vertices who are not in the complement, all of the edges in the graph have to touch one of those vertices. Why? Because the only edges that wouldn't touch any of the vertices in the complement of the independent set would have to be between vertices in the independent set, and they're an independent set, so those edges aren't there. So the complement of an independent set is a vertex cover. Okay? Now, suppose we take, if you take a maximum vertex cover, so if you take the smallest, the largest independent set, does that mean that the complement has to be the largest independent set, the complement has to be the smallest vertex cover? Yes, because if there were a way to get rid of one of the vertices in the vertex cover, then it could not share an edge. So suppose you take the largest independent set, and then you look at a vertex that you could take out of the vertex cover. So actually, I'm just showing that it's minimal, not minimum, but it is minimum. Then if there were a vertex in the vertex cover that you remove from the vertex cover, then it couldn't share any edges with the independent set, because otherwise it would have, when you removed it from the vertex cover, you would have an edge between two vertices not in the vertex cover, and that breaks the rules. So you would be able to increase the vertex cover. So it's actually, you get, so it's actually, I just argued that it's minimal, but it's actually minimum. So does G have a vertex cover of size K? Well, you can answer that problem by saying, well, does G have an independent set of size n minus K? Are people following? Okay, one person. Anyone else? So, okay, so you can reduce, okay. Oh yeah, okay, so you can reduce clique to independent set and independent set to clique, and you can reduce independent set to vertex cover and vertex cover to independent set. And so far, we haven't done anything really complicated, okay? In this case, we don't change the graph, we just change K. And to change clique into independent set and vice versa, we just take the complement of the graph. So nothing fancy. Now we get into something a little bit trickier. Okay. Oh, I should have left clique up there. So now, suppose, does anybody remember what clique looked like? Rats. Oh well, doesn't matter. So now we're going to show that you can reduce clique to a problem called SAT. Okay. So this is clique to SAT. So this is a problem. I have these reminders to myself over here, but that prevents me writing really big. I'm going to remember how this works. So clique reduces to SAT. What was the graph? It was like this. I don't know, it doesn't really matter. It looks something like that. Okay. A, B, C, D, E. Okay, so SAT, this is an instance of clique. So G, and you have K, maybe it's equal to 4 at the moment. Okay, so what you want to do is take this graph and write it as a Boolean formula in propositional logic. Okay, so I think you've seen propositional logic, right? I hope. Somebody? Maybe? Good, good, good. If then it's, so I'll write the formula for this. So let's suppose what we're going to do is write a variable which is x sub whatever if that vertex is in the clique. Okay? So we're going to say X sub A if A is in the clique. So now, so we have X sub A is true if A is in a clique. So what I can write is that if XA, so it's more particularly, I can say if XA is in the clique, then XD cannot be in the clique because they're not connected, right? So it's not XA and XD. And not X, so XA, actually I've lost a vertex somewhere, but it doesn't matter. In this graph, it's a bit simpler. Okay, and B is connected to everything, and E is connected to everything, and actually pretty much everything is connected. Oh yeah, actually, try. That's, okay, let's erase this edge, just to make things a bit interesting. And, oh no, let's erase this edge. Yeah. So that way, and not XA and XE, and now we want to say that we want at least 4 of these things to be true. So I have to remember how do you, oh yeah, so this is a little bit like dynamic programming. What you're going to say is you want to write a formula that says 4 of these variables are true, meaning that 4 of your vertices, at least 4 of your vertices are in the clique. So what you have is a new vertex, which is say Y, and Y keeps a count of how many vertices you have up to a certain point. So let's consider these in order. So what you're going to do is write Y, so if XA and Y let's see. Okay. You have vertices Y, Y0, Y0A, Y0B, Y0 something, and you have Y0A and XA do Y1B. So this is implies. And Y1A, you can't have Y1A and actually this is a double implication. Okay, sorry. It's not getting off to a great start. So what you want is you write, you have these variables. It's like the dynamic programming where you say, okay, if I want to say, can I have when I get to D, so if I process A, B, C, D, when I get to D, can I already have, say, 3 vertices in my clique? Okay. So you understand for each edge that's not there, I'm going to put a little thing that says, I consider the endpoints of that missing edge, and I say, if one of these guys is in the clique, the other one isn't. Okay, so I can't have both XA and XD. And I can't have XA and XD, I can't have XA and XE. Then I want to have this formula that says at least 4 of XA, XE are true. So if I could have this thing, if I could write this as a formula, then I would have a formula such that the formula is satisfiable if and only if there's a clique of size 4 in the graph. Okay? So the thing is, I could write a formula just by going and enumerating all the possibilities, all the possible subsets, but that's not going to be polynomial size. That's going to be exponential size. So instead, I have to come up with this sneaky way of saying that I want at least 4 of these to be true, but using only polynomial time to write it. So skipping over that, but I'll send notes to the scribes. What you would do is say, okay, well, I'm going to have sort of a grid of variables. Okay, let's go through this. So let's consider it like dynamic programming. So this is going to be XA, XB, XC, XD, XE. And here it's going to be my count of how many variables here have been set to true. So how many things are in my clique so far? And here I'm going to write, okay, if XA, and actually I'm going to have, this is going to be 2, 3, 4. Here I'm going to have a variable for each. Why is this so big? Okay, because here, this is going to be Y0A, and this is true if and only if, okay, well, actually, let's put this to be empty. So this is Y0 empty, Y1 empty, Y2 empty, Y3 empty, Y4 empty. I'm going to run out of time. Okay, so Y0 empty is true. Okay, I can set that. But Y1 empty is false. Down to Y4 empty is false. Because I cannot get one one of variable true of no variables. Okay? Now, here I have y1a. So y1a, where do I have more space? So y1a, this is true if and only if xa, well, y0a and xa. So this, if and only if, in the propositional logic, you write this as this double implication, right? Is anyone following? So y is going to be, y is going to be a variable, so I'm going to have y ij if I can set I of x, xa, xj true. Okay? I'm just, so normally the y stuff, people don't do this because they use Cook's theorem. But I want you to see how this works before we do Cook's theorem. So what I'm trying to say is, before I consider any of the variables, I cannot get a variable to be true. I cannot get one variable to be true. I cannot get two variables to be true. I cannot get four variables to be true out of no variables. But I can get zero variables out of no variables. So what I'm trying to do is this part, a formula that says at least 4 of xa through xe are true. So I have to choose at least four of the 5 things. This formula is going to say at least 4 things are true. And here there's this condition that if xa is true, then xd isn't true. And if xa is true, then xe isn't true. It's not the case that xa and xd are true. It's not the case that xa and xe are true. So then if we can satisfy the whole formula, this has a clique of size k, of size 4. What I'm trying to do is write, given this graph and given k, I'm trying to write a formula such that the formula sort of says there is a clique of size 4 in this graph. So I can write, I'm choosing to write these variables that say is xa is yes. It's like a counter. But I can't just write a counter. I have to write this in propositional logic. And I can't just enumerate like xa, xb, xc, xd are true. xa, xb, xc, xe are true. And I can't just enumerate all the possible subsets. I can in this case because it's very small. But now what I'm doing, I'm writing a formula that says I can satisfy this, but this is true, this is false, this is false, this is false, this is false. This is true if this is true and xa is true. Okay? So let's look at y sub 3c. So that I want to set true if and only if I can get 3 things, three of the variables xa, xb, and xc to be true. So y3c, if and only if, well, y3 b, right? So if I can get three variables of a, b, and of a and b to be true, well, this isn't going to be true, but I put this in for there's a recurrence. So 3 here's no, well, yes. Ultimately, the clique is size 4. What I'm going to want is y4 e. This is going to say, this is going to be true if I can get 4 of my 5 variables from a to e to be true. But y3c is going to say I can make y3c if either y3b, I can get 3 things up to out of a and b, which is not going to be true because there are only 2 things, or y2b and xc, right? So either I can get 3 things out of b, in which case I don't care if I put xc in the clique, if I put c in the clique, or if I can get 2 things, and I can get 2 things out of a and b, and I put c in the clique. So I can get of a, b, and c, I can get 3 vertices. If I can either, I put 3 vertices, if I take a and b, if I take 3 things out of a and b, which is not going to happen, or I take 2 things out of a and b, and I take c. Okay? So this, just to tell you, but you can write this. So for each of these, how big is this graph? How big is this grid? Well, it's quadratic size. It's about n squared, right? Well, it's actually going to be n times k, because you only have to take it down to k. So this grid is going to be a polynomial size, which means when I write all of this, when I write all the formulas for x, and then I take the conjunction of all of them, so I take all and of everything, then I get a formula which is polynomial size, which I plug in here, and so this whole formula, this is the restriction that says I can't have 2 vertices that don't have an edge between them. So this whole formula, I get a polynomial size formula which is satisfiable if and only if this thing has a clique of size k. So we can reduce clique to set. Basically, we can write, given an instance of clique, given a graph and an integer k, we can write this propositional formula that is satisfiable, and it's in polynomial time, we can write this formula such that it's satisfiable if and only if the graph has a clique of size k. This is because propositional logic is fairly expressive. Right? So it's a language that's powerful enough for us to write the graph has a clique of size k, and it's a kind of a clumsy language, but we can write that, and it only takes us polynomial time to write it. I mean, it takes me like a few seconds to say it. So propositional logic is not as compact as English, but we can do it, okay? So that's the idea. Given a graph g and an integer k, you can write this polynomial size formula such that the formula is satisfiable if and only if. So that's like taking This is clique to sat. The reason I write this sat, has anybody seen like, what is it, like PNG to PDF? Usually on Unix, when you do a conversion, frequently people in file format conversions, they put something to something. So that means now here, if somebody gives us, it throws in a piece of paper that has an instance of clique on it, what we want, so this is a graph G, and integer and number K, then what drops out is formula, a Boolean formula F, such that F is satisfiable if and only if G has clique of size K. So now, if somebody gave us a magic box that would tell us, given if somebody gave us this magic box, solves SAT, then all together we would be able to solve clique. If this works in this works in polynomial time. If this works in polynomial time, then dropping this piece of paper in, it will all work in polynomial time, and it will drop out a yes or a no. And this will be the answer to whether or not F is satisfiable. But because of the way we constructed this, that will be the same as the answer to whether or not G has a clique of size K. So we don't think this exists, okay? We don't think there is a polynomial time algorithm. But what we're showing is that if somebody could solve SAT, then they would solve clique. If they could solve SAT in polynomial time, then they could also solve clique in polynomial time, because we can reduce clique to SAT in polynomial time. Okay? How do people feel about this? Okay. So this is a bit messy. But actually, if you sit down and work, it's not. It gets a bit big, but it's polynomial size. Okay. So now, what we're going to do how is the blue? Can you see the blue? Okay. Sometimes I'll buy new markers. I will try black, but the black is dying. So now, oh no. Okay. Was it better with this camera? This is the little high def power shot. Okay. So now we're going to do a reduction. We want to talk about a problem called 3SAT, okay, which is SAT, but it's in what's called 3 conjunctive normal form. which means it's made up of, it looks like, so for example, this is, oh no, the black is definitely dying. Okay, that's my next thing to do. I've got the camera, I've got everything, but the x1 or not x2 or x3 and not x1 or not x3 or not x4 and x2 or x3 or x4 and x1 or x2 or x4. Okay, so this, I just want to use that as a demonstration in a little while. Okay, so this is a formula in 3 conjunctive normal form. So it's made up of clauses. It's a conjunction, so it's like this clause and this clause and this clause and this clause. And each clause is made up of 3 literals, which a literal is either a variable or the negation of a variable. And so this is saying x1 or not x2, or so people know this is and, this is or, and this is not. Okay? So this form is 3CNF, 3 conjunctive normal form. So what we want to say is that given a formula, which is not in 3CNF, we want to be able to write it in 3CNF, and we only want to make it polynomially bigger, okay? So that's this thing called the Satan transformation. So this is showing that SAT reduces to 3SAT in polynomial time. So the idea, I don't have time to go through all of this in detail, but the idea is if somebody gives you a formula, so just any formula, so like x1 and x2 and not x3 and x4. So this is not in conjunctive normal form, okay? This is not in 3 conjunctive normal form. But you want to be able to take it and put it into 3 conjunctive normal form. So what would you do? You write it as a circuit, okay, where this is going to be, oh, let's say that this is an or, just to make things fun. I can never remember which is the or and which is the and. So write it as a circuit. Okay, so this actually, let's do this, because I forgot there's a not there. Okay, what we're going to show is that once something's in 3CNF, then you can reduce 3CNF SAT to clique. So I'm just going to save time, I'm just going to sketch a little bit how the Satan transform works. So what you can do is write this as, as a circuit. Consider one of the gates of this circuit, right? So here. So let's say that you have x1 and x2, and you're going to say that this wire, we're going to call this x5. So now you want to say x5 if and only if x1 and x2. So what you do, you introduce a new variable for the output of every gate. And now, so this breaks down into, that's equivalent to saying x5 implies x1 and x2, and x5 is implied by x1 and x2. So over here, I'm just going to take this one through. x5 x5 implies x1 and x2. It's not the case. So this is it's either by, if you've done formal logic. So oh wait, I wanted to do this one. x5 is implied by x1 and x2. That's the case of saying either not x5 or not x1 and x2. And so this is by De Morgan's laws, this is not x5 or not, this is not x1 or not x2. And this you can get into not x5 or. And this, because this is all an or, it's you can take the brackets away. So you get not x5 or not x1 or not x2. So this is the same as saying, and look, this part is now a disjunction of three literals. So it's not that hard to, and then you can take this one, which is the other one, and say, okay, x5 implies x5 implies x1 and x2. So then you would say, okay, this is the case, and x5 implies x5 implies x1 and x2. That's the same as saying that either not x1 and x2 or not x5. And this works out to be actually this, wait, which one did I do? Not this. Wait, I did that. That's x, it's either not x5 or, Oh, sorry. This is not, this one, this implies this, is you don't negate the x5, right? You either say either the x5 or either the subsequent, consequent, or not the antecedent. Okay, so that's this. And then this implies this is, x5 implies this. It's either not this or this. X5. It's either this or not this. And then you get x1. No, you still want to. So this is x1 or x5, and x2 or, sorry, not x5 or not x5. Let's make this bit big. Or not x5. So this, you get this down into, this is still not quite three conjunctive normal form, but it's conjunctive normal form. So you can write that x5, if and only if x1 and x2, you can write it as this and this and this and this. And so that's in conjunctive normal form, and then you can just you can duplicate variables to get into three conjunctive normal form. Okay. So just believe me, you can take any SAT formula, and in polynomial time, you can turn it into a three CNF formula, such that the first formula is satisfiable if and only if the resulting is satisfiable. Okay. I'm just going to make this a bit bigger. Why do we care? So this is what somebody just asked. Why would we want to do this? Well, because we've seen that this is what I had on the board at the beginning. Clique. So each of these arrows means polynomial time reduction, right? Independent set. Okay, so given an instance of clique, you can turn it into an instance of independent set, you can turn that into an instance of vertex cover, or you can go backwards. So you can move between any of these three in polynomial time. Okay? And then we saw that you could reduce clique to sat. Is this big enough for people to see? Anyone? Okay. Sat, you can reduce to 3 sat. That means a SAT formula, given a SAT formula, you can turn it into a 3 CNF formula that's satisfiable if and only if the original formula is satisfiable. Obviously, 3 SAT is SAT. If somebody is an instance of, is a special case of SAT. So if you can solve SAT, you can solve 3 SAT, and if you can solve 3 SAT, you can solve SAT in polynomial time, always in polynomial time. So now what we're going to do, this is the important thing. We are about to show that you can reduce 3 SAT to clique. And that's going to mean all of these problems are equivalent up to polynomial factors. So if you can solve any of them, you can solve all of them. And if you can't solve any of them, then you can't solve any of the others. If one of them is hard, they're all hard. If one of them is easy, they're all easy. So they're all sort of the same problem in different disguises. Now that's not really surprising when we're talking about clique and independent set, because yeah, obviously it's the same problem. But it is a bit surprising when I tell you that 3 SAT, if you can solve clique, you can solve 3 SAT. because those problems don't look the same. If you can solve clique, you can solve SAT. It's not surprising that if you can solve SAT, you can solve clique, because SAT is a powerful language, right? I mean, you can write a lot of stuff in Boolean, in propositional logic. But clique doesn't seem that powerful. So what are we going to do? We have 8 minutes. So I'm not going to get through everything I wanted to today. But what I want to say, I'm going to take this formula, which is x2, x3, x4. So this is going to be sort of the first time you see what people consider a real NP completeness proof. NP completeness means it's part of this group. You can get to it from these other things, and you can get from it to these other things. Okay, if it's NP hard, it means, I'll talk about that next time. I want to get through this. Or x1, x2, x4. So this is a formula in 3CNF. Okay, and I want to turn this into a graph and a number, a graph G and a number K, such that G has a clique of size K if and only if this formula is satisfied. How am I going to do that? Well, I'm going to take it and write little vertices. So this is going to be x1, and I'm going to have copies, but the labels don't matter. Not x2, x3, not x1, not x3, not x4, x2, x3, x4, x1, x2, x4. Okay, I don't put edges in between vertices in the same group. Okay, and here I put edges between vertices that can be both true at the same time. So x3 can be the same as x1 at the same time. They can both be true at the same time. It can't be true that x3 and not x3 are true at the same time, because you can't have something and its negation being true at the same time. But x3 and not x4, that's fine. x3 and x2 are fine. x3 and x3, yes, x3 can be true at the same time as x3. x3 and x4. Okay, like that. Okay, so now x2 can be the same as x1, can be true at the same time as not x1, can be true at the same time as not x3. So now x2 is the same as x2, so it can be true. It's consistent with x3, it can be consistent with x4. Okay, x1 cannot be true at the same time as x1, but it can be true at the same time as mod x3, as mod x4, as these. Okay, so I draw this graph, and I do the same thing for the others here. So for example, x2 can be connected to all of these. And x3, it can be true at the same time as not x4. It cannot be true at the same time as not x3, but it can be true at the same time as x1. It's not x1. So I do that. This graph has size polynomial in this in this formula. Now, when I do all of this, so do you understand how to build this graph? For each clause, I write down its literals, and then between the clauses, I put an edge between two literals, not in the same group, never in the same group, never for the same clause, but between two clauses, I put an edge if the literals are not the negations of each other. Okay, and then, so this is my graph G. So I have a bunch of edges here as well. Then what I ask is, does this have a clique whose size is the number of clauses? Right? Because if it has a clique whose size is the number of clauses, that means I can choose one of the literals from each clause, and they can all be true at the same time. So there is a satisfying truth assignment. There is, so here it's going to turn out that if I do, for example, x1, and not x3, and x4, for example, I can have x1, not x3, x4. These two would be consistent. There would be an edge here. There would be an edge here. There would be an edge here. So I can choose those. I'm getting one literal out of each clause. So I have to be satisfying all the clauses. So this and this and this and this, since these are the or of these and or of these and or of these. So I'm satisfying all the clauses. So this whole and, this whole conjunction is true. And I'm not setting anything. I'm not saying, well, I'm getting x, not x3 and x3 at the same time. So there is this clique. These are consistent. And lo and behold, that means I get x1 and not x3 and x4 and x4. So if there is this clique, it means that those literals can be satisfied at the same time. And if I have a satisfying truth assignment, it means there has to be a clique. So that's how I can, given a formula in three-sat formula, I can turn it into an instance of clique. So now, if somebody gives me a magic box that solves clique in polynomial time, I can solve sat and 3-sat in polynomial time. In fact, if somebody gives me a magic box to solve any of these in polynomial time, I get sort of all of the others in polynomial time for free. So what I wanted to show was also that you can reduce Hampath to sat, but I'm out of time, so it's going to have to wait. You can also reduce Hampath to sat, and what's kind of weird is you can do a trick like this, and you can reduce 3-sat to Hampath. It's so that's another of these classes. This one is you can find on the internet, and then wow, I didn't get through as much stuff as I wanted to today. So do people start to see that, I mean, this polynomial equivalence of all these problems, these are easy and obvious. This one was not so unexpected. This is sort of a classic result from logic, and it's not too hard. This is not too hard, but it is a bit surprising. Wait, because all these edges. Okay, so it's not, is converting the set to the graph polynomial? Yes, it is. Because look, how many edges can there be? So here, how long is this formula? So if you have k clauses, it's going to be about 3k. Okay, so this is going to be at most quadratic, right? Because for each the number of vertices here is the number of the number of vertices here is basically the length of this formula. Okay, because you're going to have literal symbol, literal symbol, literal symbol, 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 literal symbol, symbol. So the number of vertices here is going to be the size of this formula. And then the number of edges is at most quadratic in the number of vertices. So it's a bit ugly. Usually people do this with 3 clauses because then it's a bit nicer. But it's not linear. It's not as easy as the complete independent set to vertex cover, but it's quadratic. So it's polynomial. Okay, I'm out of time. People are still here. Any more questions? So in this class, so far all we've said is this class SAT is sort of obviously complete for the class. If you could solve SAT, then you could solve lots of other problems for which you can write a SAT formula. They're not impossible. Okay, you can definitely do them. For example, you can clique. You can do in time n to the k. K is bounded by n, so it's bounded by a most like n to the n, right? SAT, you can just try every possible truth assignment. So it's exponential. If you have n literals, n variables, you can try it in time. Like there are 2 to the n truth assignments, you can just check them all. Remember, this was like 3-colorability at the beginning of the course. We just we counted all the 3 colorings of Nova Scotia. You can do it. 3-colorability is also in this class. So we're going to show that 3-colorability reduces to SAT because you can do basically the same trick that we had we can write a formula to see whether a graph has a clique. You can also write a formula that says, does this graph have a 3-coloring? So 3-colorability reduces to SAT. You can also show that 3-SAT reduces to 3-colorability. So I'll do that next time. So so they're not impossible. There are problems. There exist problems that are formally impossible, and we can prove it. But these aren't. These are just, we don't have a polynomial time algorithm for them. And if you came up with a polynomial time algorithm for one, you come up with a polynomial time algorithm for all of them. And so they're all sort of the same problem in various guises. They're all polynomially equivalent. And not most, well, a lot of natural problems are either we can do them in polynomial time, or they turn out to be in this class. So these problems are all what's called NP-complete. So we'll get more into that. So we're going to have to take a few more classes than I was planning. But yes. So I may have to give some help to the scribes for this lecture. About, for example, that table for how to do that, how to fill in that table. It's not that bad, but I can type that up. I just have to get a few things done. Any other questions? So the reason why we think these things are impossible is not impossible. The reason why we think there isn't a polynomial time algorithm. We've looked really hard. We've never found a solution for any of these. And in fact, we can show that if you could solve any of these in polynomial time, then it would have really drastic implications for what can be solved. It would solve just not only the problems we've considered, it would solve all problems basically any problem for which you can check a solution in polynomial time, you'd be able to find a solution in polynomial time. And that would be surprising. So, okay, next time I will do three colorability and some other things. Okay, so I didn't get to three colorability this time. Everybody okay? Okay, this was a bit of a rough lecture, but I hope the recording went okay. Okay, good. So see you Wednesday. Thank you. Okay, stop.